Okay, now we will just see the relationships between the various elastic constants like Young's modulus, rigidity modulus, bulk modulus, and Poisson's ratio. So first of all, let us take the relationship between Young's modulus and rigidity modulus. I have taken the notations as capital E and capital N. So you will have the relationship between Young's modulus and rigidity modulus. So as per definition, you know that rigidity modulus is equal to, or modulus of rigidity is equal to shear stress by shear strain. So we have got here N is equal to tau by phi, shear stress by shear strain. So again we are using the same block ABCD of side equal to unity, and it is being subjected to a shear stress tau like this. Now in order to, I have told you, whenever you apply a shear stress on one face, it cannot exist on its own. So if this is here towards right, there will be a shear acting towards left here, which will produce a clockwise moment. So by the principle of complementary shear stress, there should act a shear stress upward here and downward here, so that this will counteract their clockwise moment by creating an anti-clockwise moment. So now you have got again the state of simple shear in this particular block, but for convenience in calculations, we are saying that the face CD is considered fixed. The bottom face is considered fixed, so that it cannot move about this particular face. So it can slide only in this particular direction. So this ABCD, now it is in the position A dash, B dash, C D. So this is the new position. So the shear strain phi I have marked here. Here also the strain phi I have marked here. So by principles, basic principles, shear strain I have written from this triangle ADA dash, tan phi is equal to opposite side A dash by AD, or from this side you will have BB dash by BC. So I have written here equal to, I have taken all the sides as unity, so this becomes BB dash by 1. So I have rewritten here tan phi. I have told you phi is very small, so we are approximating tan phi is equal to 5 radians. So phi is equal to tau by n. So this is equal to, again here we have taken phi is equal to BB dash. So phi is equal to tau by n from the basic first principles, which is equal to BB dash. So you got phi is equal to BB dash, that is equation number 1. Now coming to the strain of this diagonal. Now we have taken already shear strain that has been kept apart. Now we are going to find out what has happened to this diagonal BD. This diagonal BD is now, it is in the position B dash D. So I am going to now take up what is the linear strain of the diagonal DB. So what is the linear strain? Change in length to original length, right? So change in length, final length is DB dash, original length was DB. So the change in length is DB dash minus DB divided by original length is DB. Now again you have to do some approximations. For that what I have done is, I have dropped a perpendicular from B to DB dash. So from B to DB dash, which will cut DB dash at B double dash. I have taken separately a bigger one, so that you can understand that this is the bigger diagram. This is BB dash, this is horizontal. From B I have dropped a perpendicular DB dash, and again you are assuming this angle is equal to 45 degrees, right? So 45 degrees we have assumed. Now again one more assumption is coming, I will just tell you. Now I have told you the basic change in length is dB dash minus dB, but you don't have any formula to calculate dB dash minus dB. So what happens here is, you are approximating that this change in length is approximately equal to B dash B double dash, or this particular value B dash B double dash. That means if you take an arc from D, from B you just put an arc like this. I am saying that this is the change in length coming for this diagonal, that is B dash B double dash. So I am approximating that equal to B dash B double dash divided by DB. So that is what is being written here. Drop a perpendicular from B to DB dash to cut DB dash at B double dash. So again you are coming to the linear strain of the diagonal, that is linear strain is small e equal to B dash B double dash is the change in length we have assumed. So from this triangle, this is right angle triangle, this angle is 45 degrees. So this becomes a diagonal. So B dash B double dash should be equal to B dash cos 45 because this is the adjacent side from this right triangle. So what happens here is I am assuming that B dash B double dash is equal to B dash cos 45. So we have here B dash B double dash, I have substitute here B dash cos 45 divided by BD. BD is nothing but this diagonal, which is root of 1 square plus 1 square. So B dash by root 2 into 1 by root 2 is cos 45. So you get B dash by 2. B dash from equation 1 is nothing but your shear strain, that is 5 by 2. So what we have derived here is linear strain is equal to half of the shear strain. So this much derivation is 4. So prove that linear strain is half of the shear strain. Also, linear strain of diagonal BD is equal to 5 by 2. We have already proved. Phi in terms of capital N is tau by N. So we will get it as tau by 2N. Okay.